Let's do one of these problems with approach or the whatever, right? Okay, so we have got the motion of a North Pole magnet above the page, right? Notice I'm being vague, you know, is it approaching or receding? Well, okay, so let's figure this out. All right, so let's do the direction here, because actually calculating the time and all this stuff is not very hard. But figuring out this, you know, approach and recede and all that stuff is at least somewhat difficult, right? So here's this page. Let's look at it from the side, and we've got a North Pole magnet and a South Pole magnet, right? But the North Pole is facing down. That's what I mean by the motion of a North Pole magnet, and it's either receding or it's approaching, right? So that's the question, you know, which one is it doing? Well, the current is going anti-clockwise here. Okay, so as we look at this page, it's going like that. As we look down from above, certainly it's going anti-clockwise, right? Okay, it's going anti-clockwise, right? So now the question is, what type of magnet is facing up? So if you look at a page and there's current going anti-clockwise, well, wrap your fingers of your right hand, wrap them around that way. Notice that your thumb is pointing up. This means that that current is making a magnet, and the North Pole is facing up and the South Pole is facing down. Okay, now we understand that there's a North Pole facing up. Why? Well, because it's going anti-clockwise, so north would be up and south would be down into the page, right? And so now we know the answer. This magnet must be approaching. Okay, why? Well, because you always oppose the motion of the magnet. Okay, the magnet's moving, it's got to do work, it's got to create energy, right? That means it must encounter a resistance to do that, right? Okay, so the induced current resists the motion of the magnet. Why? Well, because it's making, I could generate electricity, I could light up a light. Okay, it has to do work to generate that, right? You can't attract the magnet and also light up a light bulb, right? So it resists the motion of the magnet. Okay, so the North Pole is up. That must mean that the magnet's approaching. Okay, so this is approaching. That's kind of tough, but not too tough. I know you can figure it out, right? Okay, and then ultimately our EMF, right, is going to be the time rate change of magnetic flux, right? And there's a minus sign, the change of flux over T, right? And we're assuming that this is at right angles to this, so we don't need to worry about the cosine. This ends up being NBA over T, right? N is 1. So we've got, let's see, a current of 560 milliamps. Okay, so let's figure out the EMF. That's going to be, I'm using Ohm's law here. V is IR. So that's going to be 0.560 amps. And then what's the resistance? 1.3 ohms. So let's figure that out. 1.3 times 0.56. That's 0.728. So we're going to go 0.728 volts is equal to N, which is 1. And then our B is 1.15. It changes by 1.15, right? Okay, and then our area is 0.65 squared. Why? Because it's a square. All right. Failure. Okay, let's see. And then, then the time is what we're trying to find. Okay, so this is how much the change is of B. This is the area. That's the number of windings, right? And then we're solving. This is our EMF, right? And now we're just solving for T. So I think I'm going to go this times this times this divided by that, right? So 1 times 1.15 times 0.65 squared divided by 0.728. And I get the time is 0.667 seconds. Ta-da. Thank you very much. Thank you for joining me in Blue Pen Land. Hope this helps.